In this video, we will talk about the quadratic approximation. We did learn the linear approximation, and you may probably recognize this equation as the linear approximation or linearization of the function. The formula is f of a plus f prime of a x minus a. We know that this is basically a tangent line equation, but we have this nice linearization form. And as we can see, we may approximate, we may not use the original formula, which usually is quite complicated, quite complex. We may just use the linearization because near a, yes, on relatively short interval, yeah, like the neighborhood of a, but we may see that the function behaves almost the same like the tangent line, the blue line. In this situation, function is concave up, then the tangent is placed below, then we will underestimate if we use the values on the blue line, of course, because it's below, okay? But if we would like to get some approximation on a little bit larger, wider intervals, yeah, then the linearization, we may see, will not give us good accuracy because that's the actual value, and this is the lower one is the approximation using still linearization. Or let's say for that point B, this will be the actual value, f of B, and this will be the linearization, L of B. And we can see the vertical distance is getting higher and higher. That means that's the error, which we also talk about the error. We will not talk about in this video. Okay, that's what we have. Instead of just using a blue line, which is the line, like let's look at on the right-hand side, we may use the higher order approximation. And for instance, today we will look at the quadratic, the second degree polynomial, which is not a line, it's like a parabola, but it has a curve. And at that point, it's getting actually closer. The graph, it's closer, it's more similar to the original curve. Yeah? Actually, the pink is the original curve, and that parabola above is a second order approximation. And on the larger interval, we can go a little bit wider on the left and on the right-hand side at A and use the second. We may even go further. We can use the third order approximation, the fourth order, fifth order, actually any order. But about the higher orders and above the proof of this formula, we will talk later in section 10.7. Okay, which I believe is calculus 2. Okay, that means this is the formula for today. Okay, we will just take it like it is. We will not really look at the details. We may notice is linearization plus the second order part. Second derivative is involved, the same like some error bound for the linearization. But yeah, this is the formula. F of A plus f prime of a, x minus a, plus 1/2 second derivative at a, and x minus a squared. So we did, yes. And you may probably see the pattern. If we would like to have the third degree approximation, we will add third derivative at a, x minus a cube. That 1/2, maybe it will be not 1/3, it will be 1/6. But as I said, we will get further later. Okay, that we may definitely see that the quadratic one, the parabola, will approximate, will like estimate the curve a little bit better. The accuracy will be higher. Okay, that's me. Let's look how we can use the linearization maybe, and definitely quadratic approximation. Let's look. I pick a function cosine of x, and let's just find out how the linearization looks like, how the linear approximation and the quadratic approximation looks like at 0. What are the formulas? Okay, let's start with the linearization. L of x equals to f of a plus f prime at a, x minus a. A is 0, and now f is a function, f prime, it's its derivative. And we will have f of 0, f prime at 0, x minus 0. Function is cosine. Cosine at 0 and derivative at cosine. You can all say in your head, if you're watching this video now, you probably said in your head quietly or maybe aloud, then you will learn better, negative sign of x, negative sign of 0. That means that's function, cosine, that's derivative, negative sign. And then cosine at 0 is 1, sine at 0 is 0. That's we will have 1, 0 times x, 0. And the linearization at 0, actually I will put x because it's linearization near to 0. Yeah. Near x equals to 0. It's the straight line. Actually, it's a constant. It's just a horizontal line. We will get a graph in a moment. It's that horizontal line. We know that cosine is not a straight line, not even saying horizontal. Okay, but this is straight line. 0, at 0 is y equals, I can even say y equals to 1, but it's the linearization. Okay, let's look at the quadratic. That's the formula that would be nice to remember. The first two terms are the linearization, and then the second term. The following term, the third term with the quadratic. 1/2 second derivative at a, x minus a squared, okay? Everything is at 0. Yeah. We know function cosine. We know the first derivative, negative sign. Now we will also need a second derivative. Second derivative of cosine will be derivative of negative sign. Derivative of negative sign is negative cosine of x. Negative, please notice, cosine. Okay, cosine at 0, sine at 0, that's negative, and negative cosine at 0. Cosine at 0 is 1. Another cosine at 0 is 1, sine at 0 is 0. That's when it looks like we have negative 1/2 x squared plus 1, just parabola. That's in parabola, I believe, locally at 0, that parabola will look similar to cosine. Let's see the graphs. Right, that's when I have this is y, this is x. The red curve is cosine. It's cosine of x. And then blue was the linearization. L of x equals to 1. And not bad, because locally at 0, we may approximate. That we can definitely approximate cosine with just 1. Just 1. Yeah? And then green, it's the quadratic. But we can see quadratic, the second order approximation, are much, much more accurate. Looks almost, and we can go even like further away from 0, because it's almost like indistinguishable. Yeah, we can see the green dotted line and the cosine, the red curve. And I can put the equation negative 1/2 x squared plus 1. Yeah? Okay, that's, and we will not approximate at the moment, we have another, but we can see how better approximation. Yeah? And even if we will find a third degree, it will be even better. Yeah, that means it's also nice. We may approximate cosine, trigonometric function. I can write this down by polynomial. Yeah, polynomial approximation. So I think it's really cool. Okay, example number 2. Oh, let's read what we have. Some application. Oil is leaking from uncapped well and polluting a lake. 10 days after the leak is discovered, environmental engineers measure the amount of oil in the water to be 200 gallons with a current inflow rate of 30 gallons per day. So we may notice it's some amount, yes, 10 days. That means A of T looks like it's the amount of oil. That means I can say the amount of oil. Okay, I can write this down. Amount of oil. Then A, after like T days, A at 10 will be 200 gallons. Okay, now 30 gallons per day, it's the rate. Yes, we can see it's the inflow, the current rate. It's A prime, 30 gallons per day. Okay, that's good information. Now, let's continue. The leak is slowing so that on the 10th day, and that means it was increasing, but it's slowing. So on the 10th day, the inflow rate is decreasing by 5 gallons a day each day. So based on the units, we can see we have like time, day, like squared. We may think that this is like the rate of change of the rate of change, which is the second derivative. Like if this is velocity, this will be acceleration. If the 30 gallons per day is the velocity, the speed, 5 gallons per day each day, it's the acceleration, the rate of change of the rate of change. And since it's decreasing, it's actually, we will decrease by 5 gallons per day and per day, which is day squared, like time squared. That's the units for the acceleration. Okay, that's we have lots of important information. Suppose 8 of T is the amount of oil in gallons T days after the leak is discovered. And of oil T days after the leak is discovered. And that's when you presenting your written solution for as an assignment or maybe just for fun or helping others, please put all of the details. Okay, we definitely decode all of the text. Now the question, find the quadratic approximation for A of T centered at 10. So nice, because we know the formula. Quadratic approximation is this. A of A plus A prime at A. Oh, I just saying A, but A will be 10. Okay, and then X minus A, and then this new part, 1/2 the second derivative at A, X minus A squared. Okay, I mean quadratic approximation will be 8 of 10, A prime at 10, X minus 10, 1/2 second derivative, which is the rate of change of the rate of change, and that part. And now we can just substitute. The amount of oil at 10 after 10 days is 20, then the rate of change is 30, X minus 10, and then 1/2 times -5. Okay, and we can leave it like this, or if we prefer, this will be negative, just to have, this is 30, and this will be -5/2 times that part, okay? And now part B is asking us to use that quadratic approximation to approximate the amount of oil in the lake after 12 days, at 12 days. And that's we want to know A at 12, but we don't have any formula, we just have a certain data. We will approximate by quadratic approximation, Q of 12. Wherever we have X, which actually I supposed to put T. Okay, let's keep it X. That X supposed to be T. Yeah, so I'm so connected to the independent variable X. X, let me put, this is T, because T is number of days, independent variable. Okay, so let's just put 200. I'm just copying this formula, but instead of X, which is supposed to be T, I will put 12. And that means I will copy, okay, 30 plus 12 minus 10, yeah, delta X, delta T is just 2. We're just going 2 days. And then 5/2 and 12. Oh, sometimes this happened. 12 minus 10 squared. Okay, that's what we have. 200 plus 2 times 30, 60, minus 5 halves times 4, because this will be 2. Okay, 260 plus minus 10. Yeah, you can do it, minus 10. Okay, 250 gallons of oil in the lake after 12 days. Really nice question using quadratic approximation. Okay, but this is approximation based on all of the data that we have in the scenario. This is the approximation. Okay, another one. No, I don't know if I have enough room, but let's see. You may try to pause the video at the moment. Okay, and at this moment, try to solve this and then look at my solution. You will check yourself, yeah, because just by watching or you can watch. I have example 3 and example 4. You can watch all of them for all of the 4, and then you can redo them again, yeah, with the closed eyes. I'm joking. Okay. An object moving along a straight line path has differentiable position function S of t. S of t measures the object's position relative to the origin at the time t. It is known that at the time 9 seconds, the object position is, as at 9, it's 4 feet. Yeah? 4 feet to the right of the origin. Okay, that means it's away from the origin. Furthermore, the object's instantaneous velocity at 9 is negative 1.2 feet per second. That's, we know the rate of change, the velocity. And its acceleration at the same time, at 9, of course, it's 0.08 feet per second, because it's the rate of change of the rate of change. That means it's positive, then we can say that the velocity is increasing. Just the addition comment. Use local linearity, this is also linearization, to estimate the position of the objects at the time 9.34 seconds. Okay, is your estimate from A likely? Oh, it's supposed to be an overestimate or underestimate of the actual value. Why? We do not have actual value. That means we will see. We will see if we can answer this question. Use quadratic approximation centered at 9 to estimate the position of the objects at the same point, 9.34. And then describe the behavior of the moving objects at 9. It is moving towards the origin or away from it, and is its velocity increasing or decreasing. Okay, let's start. I can maybe add additional slides. What do you think? Just not to disturb, and maybe I can add extra slide. Now you can think, or maybe you did solve the question already. Okay. So let's see what we have. Part A. Actually, let's see what we know. S of t. That's what we know. S of 9 is 4 feet. A derivative, which is actually the velocity, but derivative is nice to say. It's at 9, it's negative 1.2 feet per second. And we also know acceleration. Acceleration is the second derivative. What is acceleration? 0.08 feet per second, and again per second. That's acceleration. Okay, so we have all of the data. Maybe, oh no, we do have the amount. I mean the distance, the position at 9. We have 9. Okay, use linearity. That's linearization. Linearization is S of 9. Let me do the shortcut instead of saying A, or then S prime at 9, and then time minus 9. Now I did I say X? Again, T. Okay, That means L of t is S at 9, it's 4, plus negative, the rate of change, the velocity is negative 1.2, time minus 9. Okay, we can leave it. We can leave it like this. 4 minus 1.2 t minus 9. Now, if we would like to approximate, the distance, yes, the position of the objects at 9.34. We will use the linearization at 9.34 and just the formula. This is the blue formula. Instead of t, we will put that time. 4 minus 1.2, 9.34. 9.34 away. I mean, we have to find the difference, minus 9. Okay, 4 minus 1.2, and this is just 0.34. Do I need a calculator? 34 times 1 will be just 0.34 plus times 2, 4. I think I did the calculation before. I think it's this one, and then when we subtract, will be 3.592, and this is just the position feet. Okay, that means this is the approximation of the position of the objects. 0.34 seconds later, after like 9 seconds. Okay, but we can see I did use the not quadratic. I used the linearization. Okay. Okay, now we can actually maybe answer still on this slide. Is this estimate over or under estimate of the actual value? We don't know, because the actual value, actually what we did the linearization. This is the actual value, and we don't know. But we may think, if this is time and this is the position, and the situation is at 9. At 9, it's 4 feet, because this is time in days, no, in seconds, and the position is in feet. And we don't have the graph, the formula, but we have that data. But what we also know, we know that the first derivative, the velocity, is negative. If the first derivative is negative, function is decreasing. But we also know that the second derivative is positive. If the second derivative is positive, function is concave up. That means concave up means like this, but decreasing. That means it's probably the situation, the graph, this is for, will be something like this. I don't know, but it's decreasing, as we can see, and concave up. This is just the rough like estimate how the position graph function, the behavior looks like. That means this is the function S of t. And what is important, concave up. Then definitely our tangent line, the linearization, because this is the tangent line, will be placed below. And if it's below, tangent line is placed, this is the linearization. If it's placed below the curve, then we using, this is the value on, yes, this is the value on for that point, 9.9 9.34, but I cannot write really low. Okay, now I cannot even 9.34. Let's write a little bit higher. We did, yes, this is the blue dot. That means it's the point on the tangent line. It's below the curve. It's underestimate. That's we definitely underestimated. Okay, that's please make sure that you can draw some conclusion based on the first and the second derivative. And that's what we learned actually for the application of the derivative. That's we did underestimate. This is the underestimate. And we know why. Because of this derivatives, concavity, and monotonicity. Okay, part C. Use quadratic approximation centered at 9 and estimate the same, 9.30, 9.34. Okay, I will change the slide for the part C, and let's write the quadratic. First of all, quadratic. S at 9 plus S prime at 9, t minus 9 plus 1/2 second derivative at 9, t minus 9 squared. And this is the linearization. Okay, that's, we know that. Plus 1/2. Oh, we can actually find out. Let me put this. That's what was the linearization? 4 minus 1.2 t minus 9, and then 1/2 plus 0.08 t minus 9 squared. Okay, that means this is the quadratic. Can maybe use green color. Quadratic approximation formula. Okay, am I right? 1.2, everything is negative, and the acceleration was positive because it was concave. Okay, now we would like to approximate at 34, and now we will use quadratic Q. Okay, 4 minus 1.2. Okay, 9, 1 second. Oh yes, I'm right. 9.34 minus 9 plus 1/2 times 0.08, I can say 0.02 because it's half, and then 934 minus 9 squared. And we may, we actually know that number because it's the linearization, 3.592. 592, and then this one 0.4 and 0.34 squared. Okay. I did use the calculator and I got 3.596624. Okay. That means this is the quadratic approximation. It's parabola, it's actually, and we may see the leading coefficient of the parabola t squared is positive. That means it's parabola open up, and makes sense because function is concave up. That means it will kind of like match when we come back. I don't know linearization, that means the parabola, maybe, I don't know, maybe somewhere here, yeah, the better approximation. And we can even see we are a little bit, yes, 9, a little bit higher, correct? 9.2, 9.6, that's when we are a little bit higher. My graph was good above, yes, above, but this is the rough. And this will be the quadratic approximation. Okay, that's when we have the formula. We just have to do this and the approximation. Now, one more thing, describe the behavior of moving objects at 9. Is it moving towards the origin or away? We may see the velocity, the rate of change, yes, of that 4 feet is negative. That means it's not going away, it's not increasing that distance from the origin. It's actually moving towards the origin. That means it's moving towards the origin, it's moving towards, okay, this will be the answer, not away, it's moving towards, and its velocity increasing or decreasing? We know that if the rate of change, yes, of a function, yeah, is increasing, then its derivative is positive. That means its derivative of the first derivative, which is second, is positive. Then the velocity is definitely increasing. And because this is positive. Well, we can see some theoretical parts are helping us too. Okay, and one more question. Similar, but we have the formula of the first derivative, but similar things. Again, you may pause the video and try to solve it on your own, and then compare with mine. Hopefully, we will match the solutions. Okay, for a certain function f, its derivative is known to be, and this is the formula, x minus 1 times e to the power of negative x squared. Note that you don't know the formula of f of x. Okay, that's we don't know the formula f of x. At what x value is the first derivative equals to 0? And that's the condition for the critical points. Justify your answer algebraically, but include a graph of f prime to support your conclusion. That's what I did. I actually look at Desmos. Yeah, you can always type the formula in Desmos, and we may get the graph. Then when we see the graph, we see a lot. Okay, part A. Let's do the part A. First derivative equals to 0 if this expression equals to 0. This expression equals to 0 if this is 0 or the other factor is 0. X equals to 1, and e to the power of any number will never give us 0. That's we have no solution. Empty set from that part. Okay, the only x that derivative is 0 is 1. Okay, that means this is 1, and yeah, what we have to do, graph. I can give the graph. What we will need, I think the graph one, but this is the graph. Yes, that's the graph of the derivative. That means this will be the graph of the derivative. I don't know if I can make this. Okay, the graph looks something. Oh, this is supposed to be lower. Yeah, I'm just copying. I just remember a little bit. Oh. One more time. This, and this one. Right? This is some number, this is a number, and this is that one when the derivative is 0. Okay, this is negative 1. Okay. I did actually copy these values. That means maybe we can, this is 1.36 and this is negative 0.36. Okay. And okay, that's it. I don't have any other values. I think that's the graph, and we can see that 1, I can use purple, derivative is 0. If derivative is 0 at 1, I mean, I don't know if we need this, but probably what's happened with the function? We don't have the formula for the function, but if the derivative is 1, that's the, I mean, if the derivative is 0 at 1, this is a critical point. Critical number, and at critical numbers function may attain maximum or minimum. Yeah? And so we may notice on the left hand side the graph of the derivative is negative below the x-axis. Right? That means original function is decreasing, and then on the right hand side is above the x-axis. That means it's positive, it's increasing. Then at 1 we will have local minimum, but I don't know if we need this, just in case if we have to. For the original function, yes, local minimum, function attains local minimum at 1. Okay, we have part A. Now part B. Reasoning algebraically, for what values of x is second derivative positive? What does this tell us about the behavior of the original function? Explain. Okay, that's we would like to find, having first derivative, the second derivative, where the second derivative is positive. So now let's think. If, we can still use it, maybe I can ask, if this, I don't want to say first, second derivative because that's it, but let's call it this. If this guy is increasing, we know that its derivative is positive, because if a function is increasing, its derivative is positive. I think that's the conclusion. If this graph is increasing, because that's the graph of the first derivative, its derivative, which will become the second derivative of the original function, is actually positive. That means let's find the interval where this graph is increasing. What color icon? It's actually increasing from that point to here. We can say when x belongs to, and I'm just copying this from the Desmos. You can also do this the same. From that point, negative 0.36 to 1.36. Okay? And this is the moment when the second derivative, is positive. Now, another conclusion. If the second derivative it's positive, then we also may do the conclusion that function is concave up, original function, which we don't have the graph. Function is concave upwards on that interval, on that blue interval. Okay? So we know what does this tell us about the behavior of the original function? It is concave up. That means this is maybe part B. Looks actually nice. Yeah, quite nice, quite easy. Because we have to know if it's concave up or concave down to determine overestimation or underestimation. If function is concave up, the tangent is below. Then we're doing underestimation. If function is concave down, tangent is always above. Then we're doing overestimation. Let's delete this. Remember this. Okay, assuming that f of 2 is -3, estimate the value at 1.88 by linear approximation at 2. Is this estimation overestimated or underestimated? And however, this is at 2. Oh, we have to be careful. Because 2 is, this is not a graph, but we may see function is only concave up to 1.36. That means at 2, function is concave down. If function is concave down and we're using the linearization, this is tangent, because at 2, then we will do overestimation. That's we still don't have the estimation, but we know that it's over because function is concave down. Only it's concave up on that blue, because it's increasing. I can maybe write this as function. I don't know how function looks like, but at 2, function will be concave down. This is really schematic, like really big graph that we will overestimate because tangent is above. Okay, let's use the linearization, part C. Okay, linearization, we have x. Okay, and let's say f of a. Now I can use the most generic formula, f of a, f prime at a, x minus a. Okay, that's mean linearization is at 2, f prime at 2, x minus 2. The value was -3. Derivative, what was the derivative? Derivative we can actually compute. Interesting. Yes, interesting. Because the formula, we have the formula. It's x minus 1 e to the negative x squared. At 2, will be 2 minus 1 e to the 4, negative 4. Okay, that means value of the derivative at 2 is e to the negative 4. E to the negative 4, x minus 2. I mean, this is linearization. Okay, that's linearization. And we remember it's nice to leave it that form because we will nicely see delta x. Now we are asked to do the approximation. That's we may approximate function for 1.88 using linearization. Just replacing x with 1.88 because then we see e to the negative 4, and this is 0.12, negative 0.12. Okay, and then I did use the calculator. It's negative 3 because this will be negative and negative, 0.0022. Okay, so this is the approximation, and we know that we overestimated. Okay, overestimated because function is concave down and tangent is above, and we just having a point on the tangent. Okay, and that means that's this, yeah. Linearization, and the part D is the quadratic approximation. Yeah, we're supposed to just practice quadratic, but we also practice additional things which are really careful. I mean, really important. Okay, let's see quadratic. I can say linearization, but let's do the formula. F of a, f prime at a, x minus a, and then plus 1/2 second derivative at a, and then x minus a squared. Yeah? Please also write this down. F of 2 plus f prime at 2, x minus 2, 1/2 second derivative at 2, x minus 2 squared. Quadratic approximation is -3 plus e to the -4, x minus 2, and x minus 2 squared. That do we have to do something? No, we just have to determine the formula. I mean, this is the formula. However, we need the second, or let's maybe use different color, and we will finish the session. Thank you for watching. I know that you watch. We need the second derivative, yes, 1/2, and we will need the second derivative at 2. Let's actually find out the second derivative. This is the first derivative. I will use the product rule. Okay? Second derivative of x minus 1 is 1 times e to the negative x squared plus x minus 1 times derivative of e to the negative x squared is e to the negative x squared times negative 2x, yeah? Inner function. And we may rewrite a little bit, negative 2x times x minus 1 e to the, this is f prime of x, and let's substitute 2. Let's don't simplify. E to the -4, 2 minus 1 is 1, 2 times 2 times 2 is 4, e to the -4. Okay, we will have -3, e to the -4. -3, e to the -4. Okay, -3/2, we may have this one. Okay, but we can leave it like this. Okay, that's we can see we still work a little bit of linearization, but we use the quadratic, and we even have, yes, better approximation in example number 3 and 4, because we did both. Okay, we're not doing the approximation. You may still substitute instead of x 1.88, and the approximation will be, yeah, definitely better. Okay. Thank you for watching, and make sure that, yes, you know just the formula and a little bit of application of the quadratic approximation. Thank you.